The night sky has always seemed infinite, a cathedral of stars stretching endlessly above, where galaxies drift like lanterns across a dark and silent ocean. To the eye, it is a three-dimensional expanse, vast beyond comprehension, carved with depth and distance. Yet hidden beneath this grandeur is a whisper more unsettling than any silence. What if none of it is truly three-dimensional at all? Some of the greatest minds in physics have suggested that the universe itself may be a kind of projection, a shadow of information cast from a distant surface at the edge of space and time. In this view, the stars overhead are not suspended in infinite depth, but etched into a thin, imperceptible horizon. Their brilliance, the echo of equations written far away. Our lives, our histories, even the unfolding of time, may all be the flickering light of a hologram, too vast for the human mind to grasp. The paradox is almost unbearable. How can a universe that cradles galaxies and bends light through black holes be nothing more than information? How can the solidity of matter, the flow of moments, the certainty of existence reduce to a coded pattern inscribed on a cosmic boundary? This is no invention of science fiction, no illusion crafted by imagination. It is a proposal born from the mathematics of black holes, from the strange union of quantum theory and relativity, and from the desperate attempt to resolve a paradox that once threatened the foundations of physics. If true, the world we walk upon, the cosmos we gaze into, and the lives we live may be only shadows, and reality itself something far stranger, shimmering beyond the veil of perception. The story of the holographic universe begins not with grand visions of cosmic illusions, but with the silent enigma of black holes. These celestial abysses, born from the collapse of massive stars, had long been imagined as simple cosmic traps, regions of space where gravity was so fierce that nothing, not even light, could escape. To most astronomers of the mid-20th century, black holes were curiosities of Einstein's equations, exotic but largely detached from the questions of daily physics. But within their darkness lay the seeds of one of the greatest conceptual revolutions in human thought. In the early 1970s, a young Israeli-American physicist named Jacob Bekenstein began to wrestle with a problem that defied intuition. Thermodynamics, the science of heat, entropy, and disorder, had long been the unshakable foundation of physics. Its second law declared with certainty that entropy in the universe could never decrease. Information about the arrangement of matter could never simply vanish. Yet black holes seem to mock this principle. Imagine, Bekenstein argued, throwing a library into a black hole. Every page, every word, every trace of order would vanish across the event horizon, that invisible boundary separating the known universe from the unreturnable beyond. If entropy truly measured information, then the second law would be broken. Order would disappear, and with it, the very bookkeeping of the cosmos. It was then that Bekenstein proposed a daring solution. Perhaps black holes did not erase information after all. Perhaps they possessed entropy of their own, but not in the way one might expect. Instead of scaling with the volume hidden inside, their entropy seemed to scale with the surface area of their event horizon. In other words, the information about everything that fell into a black hole might be etched upon its surface, encoded in the thin, two-dimensional boundary that wrapped its shadow. This was more than a mathematical curiosity. It was a profound shift in perspective. Entropy was not buried in the depths of the black hole. It was written upon its skin. Reality, Bekenstein suggested, might keep its records on surfaces. Not long after, another mind entered the scene. bringing with him an insight that would both deepen and darken the paradox. Stephen Hawking, using the strange machinery of quantum field theory, discovered in 1974 that black holes were not truly black. They shimmered faintly, emitting what would later be called Hawking radiation. The event horizon, under quantum laws, was not a perfect wall. Virtual particles near the boundary could separate, with one falling inward and the other escaping outward. The result was a slow leak of energy, causing the black hole to shrink and eventually evaporate entirely. Hawking's revelation electrified the scientific world. Black holes were no longer eternal prisons. They were fragile, impermanent, destined to fade into nothingness. But with that realization came a haunting question. If a black hole could vanish, what happened to the information it once held? Did the universe simply forget? Hawking argued that it did. His calculations showed no path by which the intricate details of swallowed matter could escape. To him, information was destroyed at the event horizon, lost forever when the black hole evaporated into radiation. But this conclusion clashed violently with the bedrock of quantum theory, which insists that information is never destroyed, only transformed. The conflict cut to the heart of physics itself. If Hawking was right, the pillars of quantum mechanics would crumble. The universe, long believed to be a lawful system where cause and effect could be traced with certainty, would reveal itself to be inconsistent, unreliable, capable of erasing its own memory. Among physicists, the debate ignited a storm. Conferences became battlegrounds where reputations and principles were on the line. Some sided with Hawking, convinced that information was indeed lost to the abyss. Others clung to the sanctity of quantum theory, unwilling to accept that the universe could break its own laws. What made the paradox especially haunting was its intimacy with reality. This was not a question of distant galaxies or unreachable mathematics. It was a question of whether the universe itself could be trusted to keep its own history. Could the cosmic ledger balance if its pages were torn out and burned? Through the 1970s, as the debate simmered, the idea of surface encoding began to take root. Bekenstein's insight that entropy scales with area whispered of a deeper principle. Perhaps nature herself was holographic. Perhaps information was always safer on surfaces than in volumes. What appeared as a three-dimensional collapse might be nothing more than a projection of data inscribed on a two-dimensional skin. Still, few dared to extend this logic to the universe at large. For now, it was a black hole mystery, a quarrel confined to the boundaries of collapsed stars and theoretical speculation. Yet even in its confinement, the implications were staggering. If the laws of thermodynamics, quantum theory, and relativity collided at the edge of a black hole, then perhaps black holes were not merely cosmic oddities. Perhaps they were windows into the very code of reality. By the dawn of the 1980s, the paradox had matured into a full-blown crisis. Hawking remained adamant. Black holes erased information. Bekenstein held firm to the notion that entropy lived on the horizon. And across the community, young physicists sensed that a revolution was stirring. The question of information was no longer about the fate of matter in a black hole. It was about the fate of reality itself. As the arguments sharpened, a new generation prepared to take the stage. Among them were voices that would transform Bekenstein's daring suggestion into a principle bold enough to describe the entire cosmos. The seeds had been planted. What began as a question about entropy had become a war for the soul of physics, and at its heart lay a whisper more mysterious than any calculation, that perhaps the universe itself was not what it seemed. The clash over black holes did not fade with time. It sharpened, drawing in some of the most brilliant minds of a generation. What began as Bekenstein's careful reasoning and Hawking's radical discovery soon grew into a battlefield of ideas, one that would reshape physics itself. Stephen Hawking stood on one side, unflinching. His calculations showed no path for information to escape the death of a black hole. If matter was devoured and the black hole evaporated into radiation, the imprint of what once was, a star, a planet, a human being, vanished with it. In his vision, the universe was capable of erasing memory, of breaking its own deepest rules. It was an unsettling possibility, but Hawking defended it with characteristic brilliance. Opposing him were voices unwilling to see quantum theory fall. Among them was Leonard Susskind, a young and fierce theoretical physicist who recognized that Hawking's claim, if true, would unravel the entire quantum framework. If information could be destroyed, then unitarity, the principle that the future of a system can always be traced back to its past, would collapse. Without it, physics itself would lose coherence. Susskind found an ally in the Dutch physicist Gerard 't Hooft, whose sharp insights into quantum field theory gave strength to a radical new vision. Together, they began to articulate an alternative. Black holes do not destroy information. Instead, they transform it, preserving it in a way invisible to traditional physics. The surface of the event horizon, they argued, was not a featureless void, but a cosmic ledger, recording every particle, every photon, every shred of information that crossed its boundary. This concept would come to be known as the holographic principle. Just as a two-dimensional hologram can encode a three-dimensional image, the surface of a black hole could encode the information of its interior. Reality, it seemed, had a way of projecting itself. The battle between Hawking and Susskind became legendary. Conferences were electrified by their debates. The chalkboards of Cambridge and Princeton filled with furious calculations, rebuttals, and counterarguments. To the outside world, it was a war of equations. To those who understood, it was a war for the soul of reality. Hawking remained steadfast through the 1980s and 1990s. Information, he maintained, was lost. The mathematics was clear. But as the years passed, the evidence against him began to mount, carried by the boldest extension of the holographic idea yet. In 1997, a young Argentine physicist named Juan Maldacena offered a breakthrough that would echo across theoretical physics. Working within the framework of string theory, Maldacena proposed what is now called the ADS-CFT correspondence, a mathematical duality between two seemingly unrelated descriptions of reality. On one side was anti-de Sitter space, a curved, higher-dimensional world described by string theory and gravity. On the other side was conformal field theory, a lower-dimensional universe without gravity. Maldacena showed that the two were not separate. They were equivalent. The physics of the higher-dimensional bulk was fully encoded in the lower-dimensional boundary. This was not speculation. It was mathematics. A three-dimensional world could indeed be described entirely by information written on a two-dimensional surface. The holographic principle was no longer metaphor. It was proof, a Rosetta Stone connecting the languages of gravity and quantum mechanics. For Susskind and 't Hooft, it was vindication. For Hawking, it was a wound. The arguments he had carried for decades were unraveling, undone by the elegant clarity of Maldacena's correspondence. Eventually, even Hawking conceded defeat. In 2004, at a conference in Dublin, he publicly acknowledged that information was not lost after all. Black holes, he admitted, must somehow preserve it. Yet the victory of holography in black hole physics opened a door to something far greater and far stranger. If the surface of a black hole encoded its interior, what of the universe itself? Could the cosmos, this boundless three-dimensional expanse of galaxies and stars, be nothing more than a projection of information written on a vast, distant horizon? The possibility was staggering. The discovery phase had begun with entropy, with the quiet puzzle of disorder and information. It had passed through the fire of Hawking's paradox, endured the intellectual war of Susskind and Tehoff, and emerged in the clarity of Maldacena's mathematics. But what it left behind was not certainty. It was an unsettling question. If black holes are holograms, then is the universe itself a hologram too? Physicists could no longer dismiss the idea as a metaphor or philosophical musing. The evidence, though indirect, was compelling. From Bekenstein's entropy to Hawking's evaporation, from Suskind's defiance to Maldacena's duality, a pattern had formed. Surfaces encoded volumes. Horizons remembered what they swallowed. Information was never destroyed, only projected. The implications rippled outward. For decades, black holes had been viewed as the most mysterious structures in the universe. Now they appeared not as monsters, but as teachers. In their paradoxes, they revealed the deeper architecture of reality. The discovery phase, then, was not merely the uncovering of a principle. It was the realization that the universe itself might not be what it seems, that what we touch and see, the solidity of space and time, might be shadows cast from a deeper surface, a screen beyond our perception. And so the stage was set for the next act of the mystery. The scientific community had crossed a threshold, from the paradox of black holes to the possibility that reality itself was holographic. What lay ahead was no longer the discovery of an idea, but the deepening of a question that would stretch physics, philosophy, and human imagination to their breaking point. The discovery phase had revealed something extraordinary. Black holes were not mute voids, but intricate storytellers, their horizons encoding the information of everything they consumed. Bekenstein's entropy, Hawking's evaporation, Suskind's defiance, and Maldacena's holographic proof had opened a door. Yet what lay beyond that door was not clarity, but shock, a crisis that shook physics to its foundations. Hawking's original claim had carried a devastating implication. If information could truly be destroyed inside a black hole, then quantum mechanics, the most successful framework ever devised, would crumble. At the heart of quantum theory lies unitarity, the principle that the evolution of a system is reversible. No matter how chaotic, no matter how transformed, the past can always be reconstructed from the present. Information, in the quantum world, is never erased. But Hawking's black hole seemed to tear unitarity apart. Imagine tossing a manuscript into the fire. The words do not vanish. They scatter into smoke, ash, and heat. In principle, every letter, every phrase can still be reconstructed, though impossibly complex. But in Hawking's universe, the manuscript does not scatter. It disappears. The smoke rises, the flames fade, and yet the words themselves are erased from existence. To the quantum mind, this was heresy. The shock ran deep because physics had always trusted in its own coherence. General relativity, Einstein's grand geometry of space and time, described the cosmic stage with elegance. Quantum mechanics, with its strange probabilities and entanglements, described the actors upon it. They were incompatible theories, yes, but each was internally consistent. Hawking's claim suggested something worse. that the universe might be inconsistent at its core. The implications spread like cracks through a glass pane. If information could vanish into nothingness, then the laws of physics themselves could unravel. Causality, the chain that binds events together, would weaken. The arrow of time could fracture. The very possibility of doing science, of predicting, explaining, and understanding, depended on the faith that the universe did not lie, that it preserved its own record. The paradox soon earned a name: the black hole information paradox, and with it came the first great realization that black holes were not just exotic astrophysical objects, but crucibles of truth, laboratories at the edge of physics where the deepest laws revealed their contradictions. Physicists began to understand that this was no marginal problem. It was not a detail to be patched or ignored. It was a question that cut to the root of reality. If the paradox could not be resolved, then either quantum mechanics or general relativity, or both, would collapse. The emotional weight of this realization cannot be overstated. To a community that had spent decades building these theories into temples of thought, the suggestion that their foundations might be broken was a kind of intellectual vertigo. The familiar ground of physics trembled, and beneath it yawned an abyss of uncertainty. Yet the shock carried with it a strange exhilaration, for in every crisis of science lies the possibility of transformation. The paradox was terrifying, but it also whispered of deeper truths. If black holes could break the known laws, perhaps they were pointing toward new ones. As the debates raged, the community split. Some, following Hawking, accepted the loss of information as an unavoidable tragedy. Others, following Susskind and 't Hooft, clung to the sanctity of unitarity. The conflict was not just technical, it was philosophical. Could the universe forget? Could existence itself betray memory? In the late 20th century, this question consumed conferences, filled journals, and inspired generations of physicists to seek answers in string theory, quantum gravity, and beyond. But for those living through it, the shock was immediate, visceral. The ground had shifted. The holographic principle emerged not as a tidy solution, but as a radical possibility born from desperation. If information could be encoded on surfaces rather than volumes, perhaps it was never lost. Perhaps Hawking's black hole was not a destroyer, but a projector. Yet to embrace this view was to accept something equally unsettling, that the universe itself might be holographic. And so the scientific shock deepened. What began as a crisis of entropy had become a crisis of reality. The paradox revealed that the universe was stranger than anyone had dared to imagine. It was not only that information might survive, it was that space, time, and matter might not be fundamental at all, but emergent, woven from a fabric of information inscribed on unseen boundaries. Physicists stood at the edge of understanding, peering into a mirror that reflected both wonder and terror. The laws they trusted seemed to fracture under the weight of black holes. Yet in that fracture, new light poured through. The shock then was not a moment, but an era when physics realized it had reached its limits and that the path forward would demand a rethinking of reality itself. The black hole information paradox became more than a scientific puzzle. It was a wound at the center of physics. For decades, Hawking defended his conclusion with the confidence of one whose mathematics seemed unassailable. He showed that Hawking radiation was thermal, random, devoid of structure. It carried no imprint of what had fallen in. If the black hole evaporated entirely, the radiation would reveal nothing of the past. To him, the conclusion was clear. The universe could destroy information, but to others, this was an impossibility too dire to accept. Leonard Susskind, in particular, could not imagine a world where quantum mechanics surrendered. He declared that Hawking's proposal amounted to the death of physics itself. Without unitarity, the laws of science would dissolve into chaos. The confrontation between Hawking and Susskind became emblematic of the scientific shock. Their debates were not quiet disagreements, but fierce battles, waged across conferences and papers, carried with the urgency of philosophy itself. Susskind insisted that information must somehow be preserved, hidden on the event horizon, encoded in ways invisible to Hawking's calculations. This, he argued, was the only way to save the coherence of quantum theory. Hawking countered that the mathematics left no room for such rescue. Black holes, in his view, were merciless erasers. The community split, and the paradox deepened. To some, Hawking's brilliance and authority were impossible to ignore. To others, the thought of abandoning quantum law was intolerable. The shock grew sharper as the paradox spread beyond black holes. If information could be destroyed in one corner of the universe, what guarantee was there that it could not vanish elsewhere? If the cosmos could lie, then all of physics was suspect. In the 1980s and 1990s, this realization cast a shadow across theoretical physics. Some retreated into resignation, accepting information loss as a strange feature of reality. Others pressed forward, seeking new principles that might preserve the sanctity of quantum mechanics. Out of this struggle, the holographic principle began to crystallize, not as a philosophical musing, but as a necessary defense against the collapse of science itself. The idea that a three-dimensional volume could be fully described by data on its two-dimensional boundary was shocking in its own right. But in the light of the information paradox, it seemed almost inevitable. If black holes encoded their contents on their surfaces, perhaps the universe itself was built on the same principle. Perhaps reality was always more like a projection than a substance. The speculative whispers became bolder. Could the world itself be a hologram? Could the depth and richness of three-dimensional experience arise from information written on a cosmic screen? It sounded absurd, yet the mathematics refused to let go. The scientific shock thus deepened into a philosophical one. For centuries, humanity had trusted the senses, the solidity of matter, the expanse of space, the flow of time. Now, physics suggested that these might be illusions, emergent shadows of something more fundamental. The debates raged, and the weight of uncertainty pressed heavily on the community. The paradox was not a problem to be solved overnight. It was a generational challenge. Young physicists entered the field with the knowledge that they were confronting a crisis no less profound than the revolutions of Einstein or Bohr. The air was charged with both fear and exhilaration. Hawking himself, though brilliant, found the tide turning against him. As the 1990s drew to a close, mathematical advances, especially Juan Maldacena's ADS-CFT correspondence, began to show that Suskind's insistence on information preservation might be correct. Hawking radiation might not be random after all. Subtle correlations could, in principle, encode the lost information. But long before the resolution, the shock itself had done its work. It had broken the complacency of physics. It had shown that the deepest laws could clash, that the universe could hold contradictions waiting to be resolved. The scientific shock of the black hole paradox thus stands as a reminder of the fragility of knowledge. For decades, it seemed that physics had nearly completed its grand picture: relativity for the cosmos, quantum theory for the small. But black holes revealed that the picture was torn, the canvas incomplete. This realization was terrifying, but it was also liberating. For in the cracks, there was room for new light. If the universe could not be trusted to preserve information in the ways once assumed, then perhaps reality itself was structured in ways stranger than the human mind had dared to imagine. And so, as the 20th century turned to the 21st, the scientific shock matured into a search, a quest not only to resolve the paradox, but to glimpse the deeper architecture of reality. The holographic principle, born in the struggle, was no longer a fringe speculation. It was becoming the guiding idea of a new era. The shock had not ended. It had transformed. What began as fear had become fascination. What began as a contradiction had become a possibility. The universe, once thought to be a vast three-dimensional stage, now whispered of a hidden script written on its boundaries. And the physicists, still reeling from the paradox, prepared to follow that script into realms beyond imagination. The paradox had shaken physics to its core, but from its fractures, new pathways began to appear. Once the first shock subsided, physicists returned to their blackboards and chalk-dusted debates, determined to test whether the whispers of a holographic universe could withstand deeper scrutiny. What had begun as a desperate defense of quantum mechanics was now becoming a new framework, one that demanded investigation with rigor, mathematics, and vision. The first step came from Gerard Tooft, whose stubborn clarity pushed him to imagine a world where the paradox dissolved not through destruction, but through encoding. He argued that information must not vanish, but rather be imprinted on the event horizon itself. This suggestion, radical though it was, offered a lifeline. If black holes could conserve their swallowed histories on their surfaces, then perhaps the laws of quantum mechanics could survive intact. To many, this was almost mystical. The idea that a two-dimensional surface could contain the full record of a three-dimensional volume felt more like a metaphor than physics. But T. Hooft pursued it relentlessly, seeking mathematical foundations for what his intuition already sensed. In parallel, Leonard Susskind became the principal defender of this strange vision. He gave it a name: the holographic principle. Just as a holographic plate can hold the entire image of a three-dimensional object within its flat surface, so too might the universe encode volumes on boundaries. For Susskind, this was not poetic musing. It was a necessity to save the heart of quantum mechanics. The idea began to take shape in thought experiments and calculations. Physicists imagined streams of matter plunging into black holes, stars collapsing, radiation falling inward, photons scattering. If the holographic principle were true, then every detail of those processes was preserved at the horizon, smeared across its two-dimensional surface like ink upon parchment. The horizon was no longer an abyss, but a library. Still, the principle remained controversial. For years, it lingered in the margins of theoretical physics, a provocative possibility without decisive proof. But the 1990s would change everything. In the hands of a new generation, the holographic principle would leap from metaphor into mathematics. The decisive breakthrough came from an unexpected voice: Juan Maldacena, a young Argentine physicist working within the intricate world of string theory. In 1997, Maldacena proposed something breathtaking. Within the framework of string theory, he showed that a theory of gravity in a higher dimensional curved space, so-called anti-de Sitter space, was equivalent to a theory without gravity defined on its lower dimensional boundary. This duality, called the ADS-CFT correspondence, electrified the field. It was as if Maldacena had discovered a Rosetta Stone for physics, a dictionary that translated between the languages of quantum mechanics and gravity. Suddenly, the holographic principle was not metaphor, it was mathematics. In this correspondence, the laws that described particles in a flat quantum field could fully replicate the laws of curved spacetime. Every gravitational ripple, every black hole, every field in the bulk universe could be encoded in the lower dimensional boundary. For the first time, holography had a formal, precise incarnation. Physicists were stunned. Maldacena's work was not simply another idea among many. It was a doorway. With it, researchers could calculate problems in one framework by translating them into the other. Questions about gravity could be solved by analyzing quantum fields. Puzzles of quantum entanglement could be understood as geometry. The implications were immediate. Black holes could now be described with clarity, their information no longer vanishing, but fatefully represented on their horizons. The paradox that had haunted physics for decades suddenly seemed less like an abyss and more like a bridge. For Hawking, it was a defeat. Though he would not concede until years later, Maldacena's correspondence had tilted the balance irrevocably. For Susskind and 't Hooft, it was vindication. Their defiance had found a champion, their holographic intuition now inscribed in equations. But for the larger community, Maldacena's work raised questions far beyond black holes. If a universe with gravity could be equivalent to a universe without? If a higher dimensional bulk could be mirrored by a lower dimensional surface, what did that mean for the cosmos we inhabit? Was our universe itself the bulk, projected from an unseen boundary? Was our reality an echo of information inscribed on the edges of spacetime? The deeper investigation had begun. With ADS-CFT, physicists had a laboratory, a tool with which to probe holography. They could test it in models, apply it to particle physics, or even use it to understand the behavior of quark-gluon plasmas in high-energy collisions. What had once been an unsettling idea was now a fertile ground for exploration. And yet, the deeper the principle was tested, the stranger its implications became. The boundaries of spacetime were not mere mathematical tricks. They seemed to hold the power to generate the world within. Geometry itself looked less like a foundation and more like a product, something woven out of information and encoded correlations. By the late 1990s, the investigation had transformed the landscape of physics. The holographic principle was no longer the desperate defense of a few rebels against Hawking's authority. It was the leading framework for approaching the unification of quantum mechanics and gravity. But the investigation was only beginning. For while ADS-CFT worked beautifully in certain mathematical universes, especially in the neat geometry of anti-de Sitter space, our own universe was not so cooperative. Our cosmos was not ADS-CF, but expanding, closer to de Sitter space, curved outward by dark energy. Whether holography could stretch so far remained uncertain. Still, physicists pressed forward, driven by the promise that the paradox had revealed something profound. Information, it seemed, was never destroyed. Surfaces contained volumes, boundaries gave birth to interiors, and reality itself might be less than it appeared. The deeper investigation would continue, carried by the brilliance of mathematics and the audacity of speculation. But the principle was already clear. The universe was whispering that it was more like a code, more like a projection, than a solid stage. And the question, heavy with both fear and fascination, began to grow louder. If the holographic principle held true for black holes, could it also hold true for the universe itself? The mathematical triumph of Maldacena's ADS-CFT correspondence was only the beginning. What followed was a decade of exploration, as physicists sought to understand what holography truly meant for the fabric of reality. If surfaces encoded volumes, and if entire gravitational worlds could be projected from lower dimensional boundaries, then perhaps the deepest truths of the cosmos were written not in the stars we see, but in the invisible correlations beneath them. One of the first great clues came from quantum entanglement, that eerie bond linking particles across vast distances. In traditional quantum theory, entanglement is a mystery of probabilities, an invisible thread tying systems together. But within the holographic framework, entanglement began to look like something more, the very glue of space-time itself. In 2010, physicist Mark van Ramsdonk proposed a daring idea. What if space-time did not exist as a stage upon which quantum fields played, but instead emerged from the pattern of entanglement between quantum states? In his work, removing entanglement caused space-time to break apart, while increasing entanglement stitched regions together. The geometry of the universe, in this picture, was nothing more than the visible shadow of invisible connections. It was a staggering realization. If true, then distance, curvature, and perhaps even time itself were emergent illusions rising from the quantum bonds between particles. Reality was not built from matter at its base, but from information. The deeper the investigation went, the more holography seemed to invade every corner of theoretical physics. Researchers began to apply the principle to high-energy experiments on Earth. In the collisions of heavy ions at particle accelerators like RHIC and CERN's Large Hadron Collider, physicists produced tiny droplets of quark-gluon plasma, matter at conditions similar to those just after the Big Bang. To their surprise, holographic models describe the behavior of this plasma remarkably well. The mathematics of a universe without gravity could explain experiments in a universe with it. It was as though holography was more than a cosmic curiosity. It was a practical tool, bridging theories once thought irreconcilable. But with this power came deeper unease. If geometry were emergent, then so too were the laws we thought fundamental. Gravity, Einstein's great insight, might not be primary but secondary, a property arising from the entangled code of reality. To some, this was exhilarating. To others, it was unsettling, as though the universe had slipped further from solidity into abstraction. The holographic investigation also began to reveal connections with another unlikely concept: quantum error correction codes. In computer science, these codes protect fragile information from being lost when bits are corrupted. In holographic models, physicists found structures strikingly similar. The bulk spacetime, with all its richness, seemed to behave like information stabilized by hidden codes on the boundary. In this analogy, the universe itself was like a vast quantum computer, preserving its own memory through the logic of error correction. If true, then reality was not merely a projection. It was a computation, a tapestry of bits safeguarded by mathematics so robust that even black holes could not erase them. The cosmic ledger was written not in matter, but in logic, protected against the chaos of collapse. Yet not all was resolved. Maldacena's correspondence worked in anti-de Sitter space, a universe with negative curvature, one that curved inward. Our own cosmos, inflated by dark energy, resembled the opposite, de Sitter space, outwardly curved, expanding faster and faster. Could holography extend there too? The answer remained elusive. Still, the successes were undeniable. In models where holography applied, paradoxes melted. Information was preserved. Black holes became engines of encoding rather than erasure. And in the quiet corridors of physics departments, the whispers grew louder. Maybe the universe itself was not fundamental. Maybe reality was emergent, born from information patterns we had only begun to glimpse. The deeper investigation also illuminated the emotional dimension of science. For many, the holographic principle was unsettling because it dissolved the intuition of being. Space felt solid, time felt real, yet here was a vision of the cosmos as a shadow, a projection written on a hidden surface. But rather than diminish reality, some saw it as a revelation that the true universe was deeper, richer, stranger than the senses could grasp. In this light, the holographic principle was not reduction but expansion. It did not make the universe less real, but more mysterious. Behind every star, every black hole, every ripple of gravity, there might be a hidden script, an unseen layer of truth. By the early 21st century, holography was no longer a fringe idea. It had become one of the leading candidates for the long-sought unification of quantum mechanics and gravity. Conferences devoted entire sessions to its exploration. Journals filled with papers extending its reach. And young physicists, entering the field, did so with the knowledge that holography was the frontier of their generation. Yet amid this progress, the paradox lingered. No direct experiment had yet confirmed that the universe itself was holographic. The cosmic horizon remained silent, its code unreadable. The mathematics was powerful, the analogies compelling, but the evidence remained indirect. Physicists pressed forward, balancing on the knife edge between speculation and proof. Still, the deeper investigation had revealed something profound, that the holographic principle was not just an idea born of desperation, but a lens through which reality itself could be reimagined. Surfaces, once thought to be boundaries, were libraries. Entanglement, once thought to be a mystery, was the foundation. Geometry, once thought to be bedrock, was shadow. And from these revelations arose a question, larger than black holes, larger than mathematics. If our universe is a hologram, what is the surface upon which it is written? Where lies the cosmic horizon that encodes the totality of existence? The answer remained hidden, but the investigation had shown enough to transform physics. The holographic principle was not a passing storm. It was the dawn of a new way of seeing. The deeper physicists ventured into the holographic principle, the stranger the universe began to look. What had started as a desperate rescue of quantum mechanics from Hawking's paradox was no longer a defensive maneuver. It was becoming a vision of reality, so radical that even those who championed it hesitated at its implications. For if the holographic principle was right, then space-time itself, the great canvas upon which all of physics is painted, was not fundamental. It was emergent, woven from the fragile threads of information. This realization marked an escalation in the mystery. Black holes had been the teachers, showing that surfaces could encode volumes. Maldacena's mathematics had given the idea precision. But the principle refused to remain confined to the horizons of black holes or the neat boundaries of anti-de Sitter space. It spread outward, seeping into the very notion of what it means for the universe to exist. One of the most provocative insights came again from the study of quantum entanglement. The geometry of space-time, long believed to be the immutable stage of existence, began to reveal itself as a construct. Then Ramsdonk's work had shown that when entanglement was removed from holographic models, space-time itself unraveled. Regions of the universe disconnected, as though the fabric of reality was nothing more than the tapestry of correlations between quantum states. The metaphor was haunting. Space-time was no longer bricks and mortar. It was the shadow of invisible bonds. Like threads in a cosmic loom, entanglement wove together the distances and shapes we call space. Remove the threads, and the universe dissolved. This was not the solidity humanity had once believed in. It was fragility, an architecture of illusion. Yet it explained why black holes could store information without destroying it. They were not erasers, but mirrors, their horizons projecting the encoded network of entanglements. As the implications sank in, physicists realized they were confronting a universe that behaved more like a quantum code than a mechanical machine. In the mid-2010s, researchers discovered striking parallels between holographic models and quantum error correction codes, mathematical systems designed to protect information from corruption. These codes, used in quantum computing to preserve fragile qubits, mirrored the way holography stabilized spacetime itself. It was as though the universe had built-in protection, a safeguard against erasure. Even as matter collapsed into black holes, even as entropy rose, the underlying information was preserved in patterns that could not be destroyed. The cosmos was not careless, it was meticulous, ensuring its own memory. This discovery deepened the mystery rather than resolving it, for it suggested that what we call reality is less like a natural landscape and more like a computation, a system preserving itself through hidden logic. Space, time, gravity, all of it could be emergent phenomena, stabilized by an informational code humming beneath the surface. The escalation unsettled even seasoned physicists. The holographic principle, once a radical defense of unitarity, was now reshaping the ontology of the universe. What was once thought to be bedrock, distance, geometry, causality, looked like an epiphenomenon, the shadow of deeper mathematics. Philosophical questions pressed harder. If space-time was emergent, what did that mean for time itself? Was the flow of moments only the unfolding of correlations in an unseen code? If space was not fundamental, then what of motion, locality, or even identity? The shock of the paradox had already broken trust in physics' foundations. The escalation forced physicists to reconsider what it meant to call something real. The mystery also expanded into cosmology. Could holography explain not only black holes, but the entire universe? If so, where was the boundary that encoded our cosmic interior? Some speculated that the cosmic horizon, the spherical boundary beyond which we cannot see, limited by the finite speed of light, might play the role of the black hole horizon for the universe itself. If true, then the totality of reality might be written on that distant screen, its code projecting the three-dimensional world we inhabit. This was both awe-inspiring and terrifying. Awe-inspiring because it offered a way to unify the deepest laws of nature under one principle. Terrifying because it stripped away the comfort of solidity. The stars above, the earth beneath, the flow of time, all of it might be emergent, a projection, a fragile tapestry of information. The escalation of the mystery also fractured the community anew. Some physicists embraced holography wholeheartedly, convinced it was the best path to quantum gravity. Others resisted, wary of reducing the universe to code. The debates echoed those of Hawking and Susskind decades earlier, but now with higher stakes. This was no longer about black holes alone. It was about everything. Yet the mathematics continued to deliver. ADAS-CFT provided tools to study quantum systems too complex for traditional methods. It described plasmas, condensed matter systems, even hints of quantum chaos. Everywhere it was tested, holography seemed to whisper the same truth. The universe plays by rules written on its boundaries. And so, what began as paradox escalated into a profound mystery. The holographic principle was no longer an idea to patch the cracks of physics. It was a window into a deeper order. Through it, physicists glimpsed a universe where space and time were shadows, where information was indestructible, where reality itself was computation. The escalation did not resolve the enigma, it deepened it. For every answer revealed new questions, each more unsettling than the last. What was the nature of the code? Where was it written? Who or what ensured its perfection? The mystery had grown beyond the walls of physics departments. It had become philosophical, existential. Humanity had always sought certainty in the solidity of the world. Now physics suggested that solidity itself was an illusion. The universe was not the stone cathedral it appeared to be, but a shimmering hologram projected from unseen depths. And the question lingered, heavy as silence. If reality is a projection, what lies beyond the screen? The realization that space-time itself might be emergent was unsettling enough. But as physicists pressed deeper into the holographic principle, they uncovered implications even more radical. If space could be woven from entanglement, then what of time? Could the arrow of moments, the ceaseless flow that carries birth to death, cause to effect, also be nothing more than a shadow of information? Time, after all, had always been elusive. Einstein showed it was relative, stretching and bending under gravity's weight. Quantum theory treated it as a backdrop, a parameter against which probabilities played. But holography whispered something stranger, that time might emerge from correlations in quantum states, just as space did. If so, then the past and future might not flow at all. They might simply exist as part of the code, written into the architecture of reality. This deepened the mystery to an almost unbearable level. The solidity of the present, the inevitability of memory, the hope of tomorrow, all could be illusions of emergent order. To many physicists, this was exhilarating. To others, it was terrifying, for it blurred the line between science and philosophy, reality and perception. The escalation was not confined to abstract mathematics. Cosmologists began to ask whether the entire universe could be understood through holography. If black holes encoded their contents on horizons, perhaps the cosmos itself was encoded on its cosmic horizon, the spherical boundary defined by the speed of light and the age of the universe. What we perceive as galaxies scattered across space might, in this vision, be projections from that distant screen. This raised another unsettling possibility. If the cosmos is holographic, then everything we experience, stars, planets, even consciousness, might be the echo of information written at the edge of space-time. Our lives could be patterns in a code too vast to comprehend. Some physicists dare to extend the principle further into the realm of the multiverse. If holography was true for one universe, might it apply to many? Could countless cosmic screens encode countless realities, each projecting its own shadow of existence? The mathematics did not forbid it. The mystery only widened. But with every escalation, resistance also grew. Not all physicists were ready to accept that space, time, and matter were emergent. Some argued that holography was a useful tool, a mathematical trick, but not a literal description of reality. The debates echoed those of Hawking and Susskind decades earlier, but with new intensity. What was at stake was no longer the fate of information in black holes. It was the meaning of existence itself. Yet the successes of holography were difficult to ignore. It continued to illuminate phenomena once thought opaque. Quark-gluon plasmas behaved as though described by holographic models. Quantum chaos, a field probing the unpredictable edge of systems, found echoes in holographic frameworks. Everywhere it was tested, holography seemed to work. Still, the escalation left the greatest questions unanswered. If the universe is a hologram, then where is the screen? What is the nature of the code? And why should reality, with all its richness, emerge from such abstraction? For some, the mystery took on a spiritual resonance. If the universe were a projection, then perhaps it was akin to Plato's cave, shadows on the wall of a deeper truth. Physics, in this view, was not diminishing reality, but uncovering its hidden layers. The stars were no less beautiful for being shadows. They were more so, because they pointed to something greater beyond. For others, the implications were unsettling to the point of despair. If time and space were illusions, then what of meaning? If consciousness itself was encoded, then what did it mean to live, to choose, to feel? Was free will a shimmer of the code, or something transcending it? The escalation did not answer. It only deepened the questions. By the early decades of the 21st century, physicists found themselves in a landscape transformed. Holography was no longer the radical speculation of a few rebels. It was central to the search for quantum gravity. Maldacena's correspondence had become a cornerstone of theoretical physics. Entanglement had become not a curiosity, but a foundation. And yet, for all its progress, holography remained unfinished, its ultimate implications still hidden. The mystery had not grown simpler with deeper investigation. It had grown stranger, more unsettling, more vast. Black holes had once seemed the greatest puzzles of the cosmos. Now they looked like messengers, pointing beyond themselves, urging humanity to reconsider what it means for something to exist. The escalation, then, was not only scientific but philosophical. It forced humanity to confront questions once left to poets and mystics. What is reality? What is time? What is the self? And are we, in the end, shadows dancing on the walls of a cosmic screen? No physicist could yet answer, but the escalation ensured that the question could no longer be ignored. The holographic principle had transformed from a desperate attempt to save quantum mechanics into a lens through which the universe itself looked unfamiliar, fragile, and profound. The mystery had deepened beyond return. The escalation of the holographic mystery had left physicists standing at a precipice. Black holes no longer seemed like isolated monsters lurking in distant galaxies. They had become laboratories, teaching humankind that information could be preserved on horizons, that space and time might be emergent illusions, and that the cosmos itself could be a hologram. But if this were true, what was the deeper machinery that allowed such a universe to exist? What were the theories that could sustain so audacious a vision? The first and most powerful candidate was string theory. Born in the 1970s as an attempt to unify the fundamental forces, string theory proposed that the most basic constituents of reality were not particles, but vibrating strings of energy. Their harmonics gave rise to the zoo of particles we observe: electrons, quarks, photons. But string theory demanded more than the familiar dimensions of space and time. To work consistently, it required 10 or even 11 dimensions, curled and hidden beyond perception. It was within this strange landscape that the holographic principle first found a precise home. Maldacena's ADS-CFT correspondence was a triumph of string theory, showing that an entire world with gravity, the bulk, could be encoded in a lower dimensional world without gravity, the boundary. It was as if the mathematics of string theory itself whispered that reality was holographic at its core. Yet string theory was not the only voice. Other frameworks attempted to capture the same truth. Loop quantum gravity, for instance, sought to quantize space-time directly, building geometry from discrete loops rather than strings. Its defenders argued that holography might emerge from these structures too, though without the elegance of ADS-CFT. The competition between these approaches reflected not only the search for equations, but the hunger for a unifying vision of reality. Within the string theory community itself, the implications of holography were startling. If gravity in a bulk space could be described entirely by a boundary theory, then perhaps gravity was never fundamental. Perhaps it was always emergent, an echo of deeper mathematics. This interpretation unsettled the heirs of Einstein, for it meant that general relativity, long considered one of the crown jewels of science, might itself be a mirage, a low-energy approximation of something richer. Theories multiplied. Some proposed that the universe's expansion driven by dark energy might itself be understood through holography. Others speculated that the Big Bang was not a beginning, but the unfolding of code from a timeless boundary. Still others saw holography as a key to the multiverse, suggesting that countless cosmic projections might be written on countless hidden screens. But not all theories were so expansive. Some were sharpened into paradoxes designed to test holography's limits. In 2012, the firewall paradox erupted, suggesting that if information truly escaped black holes, then the horizon might not be smooth, but violent, incinerating anything that crossed. This was in direct contradiction with general relativity, which predicted that the horizon should be serene. Physicists debated fiercely. Was the horizon a gentle veil or a wall of fire? Holography offered ways to resolve the paradox, but it also revealed how fragile the balance between relativity and quantum mechanics remained. Other speculations reached into the realm of philosophy. Some physicists drew comparisons to the simulation hypothesis, the idea that the universe is a digital creation, like an advanced computer program. Yet careful voices pointed out that holography is not simulation. It is not the universe as software, but the universe as projection. The distinction mattered, for it reminded researchers that holography was grounded in real mathematics, not science fiction. Still, the philosophical echoes were impossible to ignore. If the universe was projection, then what was the projector? If space-time was emergent, then what was the substrate from which it emerged? For centuries, physics had sought to peel away appearances to reveal foundations, but holography seemed to say that the foundations themselves might be appearances. Speculations also reached toward consciousness. If reality was informational at its base, was mind also emergent from the same code? Or was consciousness itself part of the holographic script, inseparable from the geometry it produced? These were not questions physics could yet answer, but they haunted the corridors of scientific thought. Despite the uncertainty, one fact was clear: holography had reshaped the map of physics. It was no longer a fringe speculation, but a guiding principle. Theories and speculations radiated outward from it, each trying to capture what it meant for the universe to be holographic. Some were rigorous, grounded in equations and experiments. Others were audacious, stretching into realms where science met philosophy. What united them all was a sense of possibility. The paradox had not broken physics, it had opened it, revealing that the universe was stranger, richer, and more fragile than once imagined. And in that strangeness lay the promise of discovery. The theories and speculations of holography were not the end of the story. They were the beginning of a new one, a story in which the cosmos itself was no longer the stage, but the performance, projected from unseen depths onto the canvas of human perception. If the holographic principle was true within the neat mathematical playground of anti-de Sitter space, Could it stretch to the untidy, expanding cosmos humanity actually inhabits? This was the question that came to dominate the early 21st century. For our universe is not negatively curved and eternal, but outwardly curved and accelerating, driven by the mysterious pressure of dark energy. If holography was to be more than a mathematical curiosity, it would need to work in this de Sitter universe, not just in the elegant chambers of ADS. The challenge was immense. ADS and CFT offered clarity because its boundaries were well defined. De Sitter space is far less cooperative. Its horizon is diffuse, dynamic, expanding as the universe grows. Yet some physicists argued that this cosmic horizon might itself act as the encoding screen, holding the total information of our universe in its shifting geometry. If so, the galaxies, stars, and lives we perceive would all be projections from that distant horizon. Speculation spiraled outward from this possibility. Perhaps the accelerated expansion of the cosmos was not a brute fact of dark energy, but an emergent effect of holographic encoding. Perhaps the entropy of the cosmic horizon was the true driver of expansion, pulling galaxies apart not through a mysterious force, but through the informational logic of holography. In this view, the Big Bang itself might not have been an explosion of matter and energy, but the unfolding of a code written on the horizon of time. Some researchers push the principle into the domain of the multiverse. If one horizon could encode one universe, why not many horizons for many universes? Each cosmos, in this vision, might be the projection of information on its own boundary, a gallery of holograms flickering in the vastness of a higher dimensional structure. The mathematics offered no barrier. The only limit was imagination. Others turned to black hole paradoxes to refine the theories further. The firewall debate remained unresolved. If information escaped black holes, did it emerge smoothly, or did the horizon become a searing wall of quantum fire? Some argued that holography demanded smooth horizons, that the projection preserved continuity. Others feared the mathematics pointed toward disruption. Each camp sharpened the paradox, hoping the contradictions would reveal the hidden rules of the code. Meanwhile, new models of emergent spacetime began to appear. Researchers built toy universes where geometry rose naturally from networks of entanglement, where connections between quantum states wove themselves into the fabric of distance. In these models, spacetime was not fundamental, but the visible shadow of invisible correlations. The holographic principle was no longer speculation. It was a working laboratory. Yet even here, questions remained. If space and time were emergent, what of causality, the principle that the future follows from the past? Could cause and effect themselves be illusions, emergent from deeper informational flows? If so, then determinism and free will alike might be shadows, shaped not by absolute time, but by the unfolding of a deeper script. The speculations reached into philosophy, drawing parallels with ancient metaphors. Plato's cave returned, its shadows now recast as quantum codes on cosmic horizons. Eastern philosophies that spoke of illusion and projection found echoes in holography's vision of emergent reality. Physicists, though wary of mystical comparisons, could not ignore the resonance. The mathematics was not poetry, but it rhymed with humanity's oldest intuitions about the unreliability of appearances. Even consciousness was drawn into the debate. If spacetime itself was emergent from entanglement, might the mind, too, be emergent from deeper patterns of information? Was awareness itself a holographic projection, bound to the same codes that generated geometry? Though physics offered no answers, the speculation haunted the edges of scientific discourse. For all its ambition, holography was still incomplete. Theories multiplied, but decisive evidence remained out of reach. Telescopes and colliders could test only fragments, indirect hints of holographic behavior in plasmas or cosmic radiation. No one had yet read the screen of the universe directly, but perhaps that was inevitable. If we are projections, then the screen itself may be forever beyond reach, an unseen horizon encoding the stage upon which we live. And yet, in the absence of proof, the theories carried weight because they worked. They dissolved paradoxes, bridged disciplines, and offered explanations where others faltered. They turned black holes from destroyers into record-keepers, space-time from foundation into emergence, and the universe from stage into projection. The speculations did not answer the mystery. They deepened it. For every model that resolved one paradox opened another. For every extension into cosmology came new questions about origins, horizons, and meaning. Holography was no longer just a principle. It was a labyrinth, pulling physics deeper into itself, daring humanity to follow. And perhaps that was its truest revelation. Not that the universe is a hologram, but that reality is more elusive than we ever imagined. That every discovery is not an end, but an opening. That beneath the solidity of matter, the sweep of galaxies, and the flow of time lies a code we cannot yet decipher, a code whose whispers reach us through black holes, horizons, and mathematics, urging us to look beyond appearances. Theories and speculations abound, but certainty remains distant. The holographic principle may prove true, or it may give way to a deeper vision still. What is undeniable is the path it has carved, a path into a universe where reality itself is suspect, and where the quest for truth is inseparable from the mystery of existence. The holographic principle had grown from paradox into possibility, and from possibility into a framework that reshaped physics. But theories, no matter how elegant, demand evidence. If the universe is a projection, then somewhere, faintly, the code must leave its fingerprints. The task for scientists became clear: to build instruments capable of detecting the subtle whispers of a holographic cosmos. A first arena of testing lay in the faint afterglow of creation itself, the cosmic microwave background. This relic radiation, released when the universe was barely 380,000 years old, is a fossil imprint of the Big Bang. Its faint ripples carry information about the earliest structures of reality. If holography was woven into the foundation of space-time, then perhaps its traces could be found etched into this ancient light. Satellites like WMAP and later Planck mapped the microwave background with exquisite precision, revealing fluctuations in temperature no larger than a few millionths of a degree. These tiny variations were the seeds of galaxies, written in the fabric of the infant universe. Some theorists propose that holographic noise, subtle departures from the predictions of classical cosmology, might be hidden within these maps. If found, such patterns would be nothing less than evidence that the three-dimensional cosmos is encoded on a distant two-dimensional boundary. The search was delicate, almost poetic. Imagine listening for the faintest vibration of a violin string beneath the roar of an orchestra. Yet the data spoke mostly of triumphs for standard cosmology, confirming inflation and dark matter. Still, some anomalies lingered: curious alignments, unexplained asymmetries, statistical oddities. To holographic's defenders, these anomalies were tantalizing hints, whispers that perhaps the universe was revealing its code in the only language it could. The next frontier was the fabric of space-time itself. If space is emergent, built from discrete units of information, then at the smallest scales, it might not be smooth, but pixelated, like the grain of a holographic film. Detecting such discreteness requires unimaginable precision, but new instruments rose to the challenge. The Laser Interferometer Gravitational Wave Observatory, LIGO, had already stunned the world by detecting ripples in space-time caused by colliding black holes. But some physicists dreamed of using similar interferometers to detect a more subtle trembling, the jitter of space-time itself, at the Planck scale. At the University of Chicago's Fermilab, an experiment called the holometer was designed to search for this holographic noise. By splitting laser beams and measuring interference with extraordinary sensitivity, the holometer hoped to reveal whether space-time quivered with the grain of encoded information. The results, so far, have been inconclusive. No decisive holographic noise has been found. But the effort marked a profound step. The attempt to probe whether reality itself has pixels, whether the smoothness of space is an illusion born of limited resolution. Even the silence of the data spoke volumes, setting boundaries on what holography could be. Meanwhile, high-energy physics offered another testing ground. In the fireball collisions at the Large Hadron Collider and other accelerators, droplets of quark-gluon plasma were produced, mimicking the early universe. Surprisingly, these exotic states of matter behaved as though they were described by holographic models. The mathematics of ADS-CFT, born in the lofty halls of string theory, turned out to be a practical tool for describing experiments in laboratories on Earth. This unexpected success gave holography a new kind of credibility. It was not only a philosophical speculation, but a working framework with predictive power. Beyond colliders, astrophysical observations continued the search. The detection of gravitational waves opened a new window, allowing scientists to probe the most violent events in the universe. Some speculated that minute irregularities in the waves' patterns might someday reveal holographic structure. Others turned to black hole thermodynamics, seeking correlations in Hawking radiation that might encode the lost information. Each experiment was a step into the unknown. The evidence remained elusive, scattered in hints and possibilities, rather than decisive proof. Yet the very act of building these instruments carried meaning. Humanity was no longer gazing passively at the stars. It was reaching for the very code of reality. The pursuit of holography demanded not only technical precision, but philosophical patience. Proof might never come as a single eureka moment. It might arrive as a gradual accumulation of whispers, anomalies in the cosmic microwave background, unexpected symmetries in particle collisions, subtle deviations in gravitational waves. Each fragment would add to the mosaic until the picture could no longer be denied. The story of tools and testing, then, is not only about machines of steel and lasers, but about a deeper hunger. For centuries, humanity has sought to know whether the universe is as it seems. The holographic principle raised the possibility that everything, from galaxies to human thought, might be projection. The instruments built to test it are our attempt to lift the veil, to see the screen upon which reality is written. And in their silence, as much as in their discoveries, they remind us of the mystery. For the absence of proof is not proof of absence. It is a call to listen harder, to look deeper, to build more sensitive ears for the song of the cosmos. The search for holography's fingerprints did not end with the cosmic microwave background or the trembling of interferometers. If the universe was truly a projection, then the task of science was nothing less than to detect the hidden script of reality. This meant pushing instruments to their absolute limits, peering deeper into space and time, and inventing new ways to interrogate the cosmos. One of the most ambitious frontiers lay in the new generation of space telescopes. The James Webb Space Telescope, JWST, launched in 2021, was designed to see farther into the past than any instrument before it, capturing the light of galaxies born less than 1 billion years after the Big Bang. While its primary mission was to study star formation and exoplanets, theorists dreamed of something greater, that Webb's data might reveal subtle anomalies, patterns inconsistent with a purely three-dimensional universe. If holography governed the earliest moments, its signatures could be buried in the arrangement of primordial galaxies, in the clustering of matter, or in the strange symmetries of cosmic light. Future observatories, such as the Nancy Grace Roman Space Telescope, and ambitious ground-based surveys like the Vera C. Rubin Observatory, promise even sharper views. By mapping the distribution of galaxies across billions of light-years, they will test whether cosmic structure follows the predictions of classical physics or carries the fingerprints of an encoded projection. But perhaps the most audacious tools are those aimed not at the vastness of space, but at the tiniest scales of existence. If space-time is emergent from quantum information, then somewhere near the Planck scale, the unimaginably small distance of 10 to the minus 35 meters, its discreteness must appear. No current instrument can probe so fine a scale directly. But physicists hope to detect indirect evidence in the jitter of particles, the limits of precision, or the correlations of entangled systems. Quantum technologies themselves may become tools for holography. Quantum computers, designed to manipulate entanglement as a resource, might simulate holographic models in ways no classical machine could. Already, researchers have built toy universes inside circuits of superconducting qubits, demonstrating how entanglement can give rise to geometry. In these delicate experiments, reality itself is rehearsed on the stage of artificial systems. What once was a metaphor, the universe as computation, becomes a laboratory demonstration, bridging physics and information science. Meanwhile, gravitational wave astronomy is only beginning. LIGO and Virgo have detected mergers of stellar mass black holes, but future instruments will reach farther. The planned LISA mission, Laser Interferometer Space Antenna, a trio of spacecraft flying millions of kilometers apart, will measure gravitational waves from supermassive black hole mergers across the cosmos. In their patterns, some physicists hope, may lie subtle deviations from classical relativity, echoes of the holographic code beneath spacetime. Other projects dream even larger. The Einstein Telescope in Europe and Cosmic Explorer in the United States are designed to push gravitational wave detection to unprecedented sensitivity. These colossal instruments, buried deep underground, will probe the whisper of spacetime at frequencies where holographic effects might be revealed. Each tool carries a kind of dual identity. On the surface, they are machines of steel and optics, cooled by liquid helium, stabilized by precision engineering. But in the philosophical sense, they are mirrors held up to reality itself, seeking to glimpse the screen behind the projection. The search has not been without disappointment. The Holometer experiment at Fermilab, once touted as a possible detector of holographic noise, reported no evidence of space-time jitter. But even in silence, the message was clear. The path would be long, the signals faint, the noise of the universe louder than its code. Science, as always, advances by eliminating possibilities as much as by confirming them. Yet the effort continues, for the stakes are nothing less than the nature of existence. If even a single piece of evidence were found, a pattern in cosmic radiation, a correlation in gravitational waves, a pixelation in space-time, it would transform physics forever. It would mean that everything, from galaxies to consciousness, is a projection, that our universe is a hologram encoded on a cosmic horizon. In the meantime, physicists push forward not only with experiments, but with theory. New frameworks attempt to extend holography beyond anti-de Sitter space, to adapt it to our de Sitter cosmos of dark energy. Others build bridges with condensed matter physics, where holographic dualities are used to understand superconductors and quantum fluids. In these cross-disciplinary ventures, holography proves itself not only as a cosmological principle, but as a universal language of physics. The tools are varied: telescopes, interferometers, colliders, and quantum computers. But the purpose is singular: to ask whether reality is what it seems. For centuries, science has trusted the senses, amplified by instruments, to reveal the world as it is. Holography challenges this faith. It suggests that what we see is not what exists, but what is projected. And so, humanity builds machines to test whether the shadows can betray the screen. The story of scientific tools and ongoing testing is, in the end, a story of humility. The universe does not yield its secrets easily. It hides them in the faintest patterns, in the deepest noise, in the smallest scales. To uncover them requires patience measured in decades, precision measured in atoms, and vision measured in philosophy. Perhaps the proof will come in the next generation of instruments. Perhaps it will never come at all. But the search itself reshapes us, reminding us that science is not only about answers, but about the courage to confront the possibility that everything, stars, space, time, even ourselves, may be shadows of a deeper truth. And in that search, even the silence of our machines becomes meaningful. For silence is not the absence of mystery. It is the voice of the cosmos saying, "Look deeper, listen harder, come closer." For centuries, humanity has trusted its senses. The solidity of the ground beneath our feet, the flow of time across our days, the immeasurable depth of the night sky, all have seemed unquestionable. Reality felt stable, eternal, unshakable. Yet the holographic principle whispers that this trust may have been misplaced. The universe, in all its immensity, may be no more than a projection, its richness encoded on a distant horizon. And if this is true, then what does it mean to be alive within it? Philosophy has always danced with illusion. The ancients spoke of shadows in Plato's cave, of fleeting appearances in Eastern philosophies that describe the world as Maya, a veil hiding deeper truths. But now physics, armed not with poetry but with equations, stands in uneasy harmony with these visions. The holographic principle does not reduce the universe to metaphor. It raises the possibility that appearances are structurally deceptive, that the world is less than it seems. This realization forces a confrontation not only with science, but with meaning. If space and time are emergent, then so too are the events that unfold within them. The rise of galaxies, the fall of civilizations, the arc of one human life, all may be patterns within a deeper code. To some, this diminishes existence, turning life into an echo of mathematics. To others, it ennobles it, for it means that our very being is inscribed on the universe's horizon, preserved forever as part of its indestructible memory. Consider what it means if information is truly eternal. Every thought, every moment, every word spoken in love or anger, every silence of grief, all of it would remain encoded somewhere beyond perception. Black holes do not destroy it. Time does not erase it. The universe in this vision is a perfect archivist. Nothing is lost. Nothing is forgotten. And yet, this permanence is unsettling. If the cosmos remembers all, where does that leave the human longing for freedom, for the chance to shape destiny? If every action is encoded, does the code itself determine us? Or do we write it as we live? In the shadows of holography, free will becomes a puzzle suspended between emergence and inevitability. The emotional weight of this possibility is profound. To walk beneath the stars, knowing that they may be projections, is to feel both smaller and larger at once. Smaller because we are shadows on a cosmic screen. Larger because those shadows are written into the deepest truth of existence. We are not accidents adrift in void. We are part of the code that sustains the cosmos. The holographic vision also challenges our relationship to death. In the classical view, death is erasure, the end of a pattern, the dispersal of matter, the fading of memory. But if information is never destroyed, then perhaps death is a transformation rather than oblivion. The imprint of a life once lived may remain inscribed on the horizon of reality itself. Physics does not promise immortality, but it denies annihilation. In the holographic universe, even endings are preserved. Still, the principle leaves unanswered questions more profound than any it resolves. If the universe is a projection, what is the projector? If we are shadows, what is the light that casts us? The mathematics is silent. It tells us that information is preserved, that surfaces encode volumes, that entanglement builds space, but it cannot tell us why. The question of origins, of purpose, of meaning lingers at the edges of science, like a horizon that recedes as we approach. For the physicists who work at the frontier, this silence is both humbling and inspiring. It reminds them that the search for truth is endless, that every discovery opens deeper mysteries. For the rest of humanity, it offers a chance to reimagine our place in the cosmos. We are not at the center of the universe, nor even solid within it. We are participants in a story projected across space-time, actors in a drama written in the mathematics of horizons. Perhaps this makes the universe less real, but perhaps it makes it more beautiful. For beauty lies not only in solidity, but in mystery. To know that reality itself may be woven from information, fragile yet eternal, is to glimpse the poetry of existence. The stars shine all the brighter when we realize they are shadows, for shadows themselves are signs of light. In the end, the holographic principle is more than physics. It is an invitation to wonder, to question, to see beyond the surface of things. Whether or not the universe is truly holographic, the principle has already transformed our imagination, forcing us to confront the possibility that reality is not what it seems. And in that confrontation, we are changed. If the universe is a hologram, then everything we know becomes both fragile and eternal. Fragile, because the solidity of the world, stone, sky, even time itself, dissolves into a projection. Eternal, because information cannot be erased. It is preserved in the hidden surface from which the cosmos is cast. This duality is what makes the holographic principle so unsettling and so profound. It invites us to reconsider the most intimate aspects of existence. The moment of a child's birth, the grief of loss, the fleeting beauty of a sunset. None of these vanish into nothingness. If the principle is true, their imprint remains encoded somewhere beyond sight, part of the cosmic archive. In this way, physics brushes against poetry, suggesting that nothing is ever truly lost. But this permanence raises haunting questions. If everything is preserved, do we live in a universe without forgetting, without release? Is time itself not a river, but a static code where past, present, and future exist simultaneously? And if so, what does it mean to make choices, to hope, to dream? Are we authors of the code, or merely actors reciting what has already been written? The holographic principle does not answer these questions. It sharpens them. It forces us to face the paradox of being human in a universe that may not be as it appears. It reveals the fragility of perception, the instability of certainty, and yet it does not strip life of meaning. For if reality is projection, then projection itself becomes sacred. Shadows are no less beautiful because they are shadows. They are proof of the unseen light. This reflection extends to our place in the cosmos. For centuries, humanity has moved step by step away from the center. Copernicus displaced us from the middle of the heavens. Darwin displaced us from the center of life. Relativity displaced us from absolute time and space. Now, holography suggests that we are not even embedded in the three-dimensional world we trust. We are written on a boundary, woven into correlations, encoded in patterns we cannot see. And yet, paradoxically, this makes us more central than ever. For if the universe is holographic, then everything, galaxies, stars, and the human heart, is equally part of the code. Nothing is excluded. Nothing is expendable. In a hologram, every fragment contains the whole. In this sense, each human life is a reflection of the universe itself, a shadow that carries within it the light of the whole cosmos. The principle also reshapes how we imagine the end. If black holes cannot erase information, if horizons preserve what they swallow, then perhaps the universe too carries within it the record of all it has ever been. The heat death of the cosmos, the collapse of stars, even the silence that may come at the end of time, none of it would erase what has been lived. The script of existence, once written, endures. This does not diminish the urgency of the present moment. If anything, it magnifies it. For to live is to inscribe the code, to participate in the unfolding of reality's projection. Each action, each thought, becomes part of the permanent archive. The fragility of perception is balanced by the eternity of inscription. In this light, the holographic principle is not only a scientific hypothesis, but a mirror held to humanity. It shows us the limits of knowledge, the depths of mystery, and the strange resilience of meaning in a universe that may not be as solid as it seems. It reminds us that science is not only the pursuit of equations, but the pursuit of understanding what it means to exist at all. And so the documentary closes not with certainty, but with wonder. The stars above are shadows, yet they guide us. The space between them is emergent, yet it holds us. Time flows, though it may be an illusion, and in its flow, we find love, loss, hope, and beauty. If the universe is a hologram, then we are its flickers of light, its shifting patterns, its luminous illusions. But illusions that feel, that dream, that question. And perhaps that is the greatest revelation of all, that even if reality is a projection, it is no less real to those who live within it. The night sky remains. Galaxies still drift like lanterns on an unseen sea. And somewhere, on the boundary beyond perception, the code of the cosmos endures, a silent script, eternal and mysterious, writing the story of everything.